Good evening, everyone, and welcome to Cracking the Cancer Code. My name is Dr. Darren Brenner, and I'm an associate professor in the Departments of Oncology and Community Health Sciences at the University of Calgary. Feel free to keep making your way down as long as you can safely see. I'm an epidemiologist and data scientist, and as a member of the Charbonneau Cancer Institute, I lead the Cancer Screening, Detection, and Risk Reduction Research Program. The Charbonneau is an exciting place. It's an institute, and it's a community of scientists and clinicians dedicated to understanding and preventing cancer, working to transform detection and treatment of cancer, and improving life with and after cancer. We're very excited and grateful to have you all join us here this evening, and it's my pleasure to welcome you to tonight's Cracking the Cancer Code series, Beyond Boundaries, the AI Revolution in Cancer Care and Research. To begin our program, I want to recognize the ancestral territories, cultures, and oral practices of the Blackfoot people. The University of Calgary, located in the heart of southern Alberta, both acknowledges and pays tribute to the traditional territories of the peoples of Treaty 7, which include the Blackfoot Confederacy, comprised of the Siksika, the Piikani, and the Kainai First Nations, the Tsuut'ina First Nation, and the Stoney Nakoda, including the Chiniki, Bearspaw, and Goodstoney First Nations. The City of Calgary is also home to the Métis Nation of Alberta, Region 3. We're very excited to see both new faces and returning faces tonight in the audience. This series, Cracking the Cancer Code, is intended to bring together researchers, clinicians, and the public to talk about the future of cancer care and how improvements in both our understanding of technology and the application of technology can bring about hope and change both today and in the future. Before we get to these fascinating talks, and very shortly, I'd like to make a note of the Own Cancer campaign, which you might have noticed the table when you walked in tonight. The Own campaign is a fundraising partnership between the University of Calgary, the Alberta Cancer Foundation, and Alberta Health Services. The goal is to raise $250 million to support the care and research vision of the newly built Arthur J.E. Child Comprehensive Cancer Center, which is set to open this fall. If you're not aware, the new center will be the largest in Canada at 1.3 million square feet and among the most impressive in all of North America. It will bring together care, services, and research all under one roof in ways never before possible. What an exciting time for all of us as Calgarians to witness this once-in-a-lifetime project and to be a part of it. The campaign is already over 90% of the way to reaching its goal, and tonight there's a great opportunity to make a donation with a double match. Until April 18th, any gift will be matched twice by the University of Calgary and in thanks to the generosity of Glenn and Aaron Rumpel. The matching is limited and while funds last, so we encourage you to stop by the table and grab a QR code on your way out and make a donation tonight. So thank you very much again for joining us tonight, and please enjoy this evening of interesting and exciting talks.
Hi, everybody. My name is Christina Frangu, and I am an independent journalist here in Calgary. I've been lucky to be your moderator for a number of these events, so thank you very much for welcoming me back. It's important to me to be a part of these discussions. Cancer has touched my life in a very direct way. As many of our returning audience will know, my husband, Spencer, who was a physician here in Calgary, died from kidney cancer when he was 36 years old. And then just a few weeks ago, cancer again has barged its way into the circle of my family, which is all to say like so many of you here tonight, I eagerly await improvements in cancer prevention, detection, and treatment. Which brings us to tonight's talk, which is focused on artificial intelligence, or AI, in cancer care. And for years as a medical journalist, I've been going to conferences hearing about AI as part of the future in cancer care. But seemingly overnight, we are suddenly here. AI is now a part of today's healthcare landscape. So tonight, we will look at how AI is being used to support patients and researchers in Alberta today. The way tonight is going to look, it's the same as it's always been. Each of our speakers is going to speak for about 15 minutes, and then they'll join me on stage for a panel discussion. And of course, at the end, we've put aside some time for you to ask your questions. So it's my privilege to introduce our first speaker for tonight, Dr. Matt Warkentin. He's a molecular epidemiologist at the Cummings School of Medicine at the University of Calgary. He specializes in the intersection of cancer epidemiology, biostatistics, and machine learning. Put it another way, and he likes to find order in chaos, is kind of the way he says it. His current research focuses on lung cancer screening programs, both provincially and nationally, and he is going to talk to us tonight about how AI is being used in cancer screening and detection. Matt.
Okay, so show of hands, how many people here use Netflix or Spotify? Looks like pretty much everybody, and you've probably noticed that when you've used those services, the more data you feed into those technologies, the more they can learn your interests and give you those perfect movie or music recommendations. And you've probably noticed how over time cell phones have evolved from basically just phones to these complex devices we take with us everywhere and that deliver to us these personalized digital experiences. AI powers those technologies and so many more. And it's probably impacted your lives many times, even just on your way here today. AI plays a major role in so many aspects of our daily lives, and we are using those very same AI technologies to improve the personal delivery of cancer screening here in Alberta. When we talk about cancer screening in Alberta, what we mean is the provincial programs that exist to detect cervical, breast, colorectal, and lung cancers as early as possible. Each of these screening programs produce complex images that allow us to find out what's going on inside the body. Whether that's 2D or 3D images of the breasts or lungs, the slides that we look at under a microscope from a Pap test, or the videos that are captured through a colonoscopy. These screening approaches generate massive amounts of visual data, and we can use AI to recognize the important patterns that enable us to find cancers before it's too late. So this all probably sounds great, but I think it really begs the question, what do we really even mean when we say AI? So let's set the stage for the definition of AI we'll use in our talks. By now, everyone here has probably heard of or maybe even used ChatGPT. So I thought it would be fun as a starting point to ask ChatGPT to create a definition of artificial intelligence specifically for this event. Okay, so let's see what it has to say. Now, it turns out this definition is perfectly fine, but we thank AI for helping us get started, but I think we can take it from here and give it a bit more of a human touch and pull out what I think are the important details of that message. Artificial intelligence is the use of advanced computer algorithms to analyze vast amounts of medical image data or medical data, identify the important patterns, and provide us with tools to assist in the delivery of personalized cancer care. So I think this definition will work just fine. But before we talk more about the future of AI, let's take a step back in time to see how we got to where we are today. It turns out that the seeds of AI were planted as far back as the late 1950s, and this was well before we had computers good enough to get us to where we wanted to go. However, this idea of teaching a computer to achieve human-level intelligence has a long history. We can fast forward to 1997, when for the first time a computer was able to beat a grandmaster at chess. Or fast forward to 2011, when IBM's Watson was able to win Jeopardy against former long-running champions. But the big bang event for modern AI as we know it happened precisely on September 30th, 2012, when a PhD student at the University of Toronto was able to teach a computer to classify 14 million images as common everyday objects. This event reignited the interest in using AI for complex pattern recognition tasks. And not only did this breakthrough event provide us with the blueprint for modern AI, but it turns out that the fundamental patterns like edges, lines, textures, colors, shapes, that a computer learns to understand all of the different objects you see on the screen here can actually help us in our quest to find the earliest signs of cancer in the body. What makes AI different than other computational approaches is that these important patterns are learned directly from the data itself, rather than this being something we have to tell the computer to look for. In other words, the models learn from experience in a manner that's very similar to how humans learn. and with achieving human or even beyond human level performance on some of these tasks, this gives rise to the notion of artificial intelligence. And borrowing knowledge and experience from different disciplines turns out to be a really powerful idea. So powerful that it's become standard practice that AI models developed for a specific task, like detecting cancers, are typically built for models that were first developed for a completely different task, like telling dogs from cats or even boats from planes. So what this means is we don't need to start from scratch every time we want to develop new AI solutions. We can leverage intelligence from other domains to accelerate cancer care into the future. Tonight, you'll hear even more about the progress and potential of AI to crack the cancer code. However, it is worth keeping in mind that while artificial intelligence does hold great promise in revolutionizing cancer care, with its potential to enhance diagnosis, prognosis, treatment planning, and personalized medicine, the development and integration of these tools into a clinical practice will still take some time, and there are still many questions that need to be answered. Okay, so I've mentioned that AI is set to dramatically improve cancer screening across the various screening programs here in Alberta. But for the remainder of my talk, I'm going to focus specifically on lung cancer screening. And so I think a natural first question is, like, why do we even need to screen people for lung cancers? Well, lung cancer is the most commonly diagnosed cancer among Canadians. And in the absence of screening, they're typically diagnosed when the cancer has spread to other parts of the body. At that point, treatment options become less effective, and the likelihood of curing that cancer decreases dramatically. And because of all of that, lung cancer is the leading cause of cancer mortality in Canada. But it's not all bad news. We can screen for lung cancers, we can find them early, and we can save lives. So let's talk about that. Lung cancer screening differs from all of the other screening programs. Everyone in this room, at some point in their life, will be eligible for screening for at least one of the other cancers that I mentioned. It's not possible to screen everyone for lung cancer, but more importantly, not everyone needs to be screened for lung cancer. But finding the right person in the population to screen is an important way in which we use AI to improve the way we deliver care. Around the world, most lung cancer screening programs are based simply on age and smoking history. But here in Alberta, we use more sophisticated models that include a richer set of information to identify high-risk individuals for screening. And why do we do this? Well, taking into account more information, more known risk factors for lung cancer, means we can make better predictions about lung cancer risk and get the right person screened at the right time. And once we've found that right person, the next step in the process is to take a three-dimensional image of their lungs using a specialized type of X-ray technology known as computed tomography, or a CT scan. But just a single CT scan for a single person can produce as much as 40 million data points, each of those containing a tiny amount of information towards the health of that person's lungs. If we think about that more broadly at the national level, screening for lung cancer can produce more than 25 terabytes of images annually and more than 10 trillion data points. AI solutions will enable us to handle this volume of data, and the AI tools we develop will allow radiologists to use as much information as possible in the most optimal way to find lung cancers as early as possible. Okay. So let's look at 4 different ways in which AI is used in the delivery of lung cancer screening: detection, contouring, risk assessment, and decision-making. Let's start with detection. The lungs are a complex organ with a network of airways that resemble the branching of a tree. And finding early signs of lung cancer in there can be like finding a needle in the haystack. So what we're looking at on the screen here is a single thin cross-sectional slice from a CT scan. You could think of it as almost like a page in a book, where the book is like an autobiography of everything your lungs have experienced in your lifetime. The black areas represent the airspace in your lungs, and the whiter areas represent the other dense anatomical structures of the body. So you might think this doesn't look all that complex, but remember, we're looking at the lungs, a thin slice of the lungs in 2D. In 3D, the lungs look more like this. And so now you can probably see why having AI as a second set of eyes can help guide us through this maze and allow us to do better at finding cancers earlier than what would be possible by humans alone. Again, here's a single slice from a CT scan, this time up near the top of the lungs. That white dot you can see inside of that yellow box is a small lung nodule that was detected by AI and brought to the attention of a radiologist. And once we've found something, it starts the process of being able to figure out what we should do next. One of the things we want to do next is to be able to precisely define which part of an image corresponds to that nodule we've found. And that'll allow us to gain a deeper insight into the 3D structure of the nodule so we can understand its cancer risk. Now, that's something that was traditionally time-consuming and done manually by a radiologist. But with modern AI technologies, we can do this faster and more accurately. Inside the yellow box on the left are 6 different lung nodules traced manually by a doctor. And in the red box on the right are 5 different AI models doing the exact same thing at the click of a button. AI can perform these tasks quickly and accurately, and by limiting the amount of time a doctor must spend on these tasks, we allow our doctors to spend more time doing the human part of healthcare. So we've seen how complicated the lungs are. And as it turns out, there are lots of things we might find in the lungs, and most of them aren't cancer. So we need to be able to accurately predict cancer risk for the things we find. In the next 4 examples I'll show, an AI tool suspected lung cancer when traditional clinical approaches did not. In this first example, the AI predicted a high lung cancer risk for this person even before an abnormality was even yet apparent to the human eye on the image on the left. And 2 years later, this person was diagnosed with a stage 1A lung cancer. In the second example, if you can look at the arrow on the left, this person had a nodule in the lingula next to their heart that was actually missed by a human upon a first viewing of this scan. But the AI tool assigned a high lung cancer risk, and 1 year later, this person was diagnosed with a stage 3A lung cancer. In this third example, the nodule on the left, based on size alone, was considered too small to trigger a 6-month follow-up, and this person was then later diagnosed, again, with a stage 1A lung cancer. And lastly, in this fourth example, that black space you see the arrow pointing to, that's what's known as a cystic airspace in this person's left lung. And a cyst-associated lung cancer is among the most difficult to recognize early. But AI predicted a high lung cancer risk, and this person was diagnosed with a stage 1A lung cancer. All 4 of these people were diagnosed with lung cancer within 2 years of their initial screen. AI and lung cancer screening may help to save their lives. When it comes to clinical decision-making, the document that you see on the left is something that we look to guide our decisions for what a person should do next after they get screened for lung cancer. But it's based on a limited set of visual information like those shown on the right. The size of a nodule, the location of a nodule in the lung, the appearance of a nodule, and whether or not it appears to be growing or shrinking over time. And based on that information, a person will be placed into one of these 4 risk groups. And then based on belonging to that risk group, they might be told to come back in 12 months, come back in 6 months, come back in 3 months, or maybe the risk is so high that that person needs to proceed right to diagnostic workup to see if they might have lung cancer. But just like with finding the right person to screen, we think we can do better with our decision making. So here at the University of Calgary and the Tom Baker Cancer Center, and soon to be the Arthur Child, we are conducting important research to improve these decision pathways. This starts with deciding who we should screen and how we should screen them by taking into account more sources of information, using innovative tools like the ones I've talked about today, to allow our healthcare team to make better decisions and ultimately be guided by improving patient outcomes, with AI being used at every step of the way. Cancer screening is one of the most effective ways to reduce the impact of cancer on Canadians. We've just seen some examples about how AI is set to improve lung cancer screening, but the use of AI in cancer screening and cancer care goes well beyond just these examples. Tonight, you'll hear even more about how AI is being used as a force for good in Alberta to accelerate cancer care across the spectrum. In the next 5 to 10 years, artificial intelligence is going to provide new paths towards improving cancer care across the continuum to deliver better personalized healthcare to Canadians. For cancer screening, this means we will get better at figuring out who we should screen and how we should screen them and get us one step closer to cracking the cancer code. Thank you.
Thank you, Matt. And I have to say, as the resident writer in the room, I really appreciated the way that you showed that human writers can still outperform ChatGPT. And if any of my students in the room are in the room, I hope you notice that. So now moving on from AI and cancer detection to AI's place at the patient's bedside. For that, we have Dr. Omar Khan, a clinical assistant professor at the Cummings School of Medicine and a medical oncologist at the Tom Baker Cancer Center. In his practice, Dr. Khan cares for patients with breast cancer and sarcoma. On the research side, he looks at how we can apply AI safely to clinical cancer care. Omar.
So, can we predict the future? This is a really, really important question, and even more so for my patients. And before we try and answer that question, let's actually go back in time. Not too far back in time, maybe about 4 hours. I was about to enter a room just like this one. And you can envision yourself being in this type of room, either with somebody you know, or maybe even for yourself. And before I walk into a room like this, I know that I'm about to meet a patient for the first time, and that we're going to be talking about a lot of data, information about their cancer, different treatment options, different tests that we may also be doing. But fundamentally, the question that the patient is asking me is, can we predict the future? But that question is much more real. It's actually, am I going to be okay? What's going to happen next? And that's much, much more real. But the reality is that predicting the future is not easy. It's fraught with error and uncertainty. And I often joke with my patients that if I could predict the future, I'd be kicking it back right now on some island somewhere, retired. But how close can we get? We know that if I had a magic pill for a patient, a treatment that had no side effects, a treatment that worked 100% of the time, you wouldn't need to talk to someone like me to actually come and get treatment. You could go to a vending machine and pick it up on your way after diagnosis. But the reality is that our treatments have side effects that can be potentially quite severe. And they're also not perfect. They don't work in 100% of patients. And so let's do a bit of a thought experiment. So imagine that you're about to decide whether or not to start a treatment to try and increase the chance of cure for a cancer that you were diagnosed with. This treatment might have side effects, for example, hair loss, tiredness, nausea and vomiting, suppressing your immune system or increasing the risk of infection. What percentage benefit or what percent increase in the chance of cure for a cancer would you be willing to take that treatment for? Would it be 1%? 2%? 5%? More than that? And then let's take it one step further. Imagine someone who you care about a lot. What percentage would you encourage them to take that treatment for? Would it be the same number that you would give yourself? So these are really, really hard questions. And a lot of times when I'm in the clinic, I'll be honest in that I don't know the answer to these questions either. We're trying to pick one of many different potential paths for patients. And we don't know exactly where those paths are going to lead. And so the very least that I can do is try and make sure that I can give them as accurate information as possible when we're trying to pick which one of these paths to go down. And this comes back to that concept of trying to get as close as possible to this crystal ball. And so how do we try in the clinic today to give patients the information they need to make decisions? The first thing we look at is something like cancer staging. And so we can say, based on what stage a patient's cancer is at, what their survival outcome or probability might be. A stage 1 cancer is one that is localized to a single organ and is quite small. At stage 2, perhaps the cancer has become a little bit bigger, but may still be confined to that one organ. By stage 3, a cancer is moving to the area around that organ, maybe to organs close by. And then at stage 4, the cancer has moved to distant parts of the body, perhaps through the bloodstream or through the lymphatic circulation. And we know that survival does depend on what stage a patient is diagnosed at. But this is still a very crude way of giving somebody an estimate. So can we do better? This is an example of a model that I use today in clinic called PREDICT from the NHS in the UK. And this takes a number of different features of a cancer, does some complicated math with them, and then tries to predict what would happen to 100 people going through treatment for breast cancer. The solid circles are people who are alive 10 years from now. The circles that are not filled in are people who have passed away. So this model can tell me what percentage benefit a different treatment may have. But what it doesn't do is tell me if my patient is this person, for whom any treatment that I'm about to give them is adding side effects without actually helping their cancer be cured, because the surgery had already done it. Or conversely, this patient, for whom none of our treatments are actually going to prevent a cancer from coming back. And that is the type of patient in whom maybe we should be looking at more experimental treatments. Can we get better than that? Instead of taking 9 or 10 variables that I can look at in the clinic, perhaps we can look at the genes that are expressed in a cancer. And sure enough, there's a test called Oncotype that we use in breast cancer. And this test looks at 21 different genes that are expressed in a cancer to see what's driving that cancer to grow. And then it comes up with a score, and the higher the number, the more aggressive the cancer is. And again, we can try and predict what the risk of recurrence might be. And I can also take that one step further to then estimate what the benefit of a treatment like chemo might be for that patient. But fundamentally, all of these models are taking certain input data points and trying to run them through a calculation. And each of those data points has a specific weight that it always gets assigned. So for example, age might have a specific factor that we multiply it by. Once we do the calculation, we try and come up with a prediction. This is a very linear or two-dimensional approach to things. So how can AI help? If we look at an example artificial intelligence model, we can take these inputs, but now we're doing a series of different calculations. Think of them as a series of those crystal balls that I was talking about before. We're still trying to come up with a prediction, but now each of these input points has a different weighting in each of these different calculations. And we can do that over and over again to try and come up with a much more complex calculation. And so now instead of saying that age always has one value that it is multiplied by in a model, we can now say, what if I combine age with the number of lymph nodes, or with how aggressive the cancer looks under the microscope? And we can actually look at these variables in combination in a nonlinear way. And then you can actually even layer that more and add to the complexity of these calculations. What I've just described is something called a neural network. And it's actually modeled after the way our human bodies work. And this is the way that our brain actually processes signals. Is this being done? It absolutely is. This is a graph of how many papers are being published in artificial intelligence and cancer care. And you can see that really where it took off is kind of in the mid-2010s, with over 6,000 publications happening in the last year. It's really important, I think, to highlight here that this is the research being done, and the research predates us being able to use things in the clinic, because we need to validate, test, retest, and really be sure before we can apply this directly to patients. But where can it help? So I'm going to step back and take an example just to show you, I think, where the power of AI can really be. So if we look at diagnosing tuberculosis on X-ray, this is not cancer, this is a lung infection. It's a contagious lung infection that, although it's decreasing in frequency, you still see it in areas of Canada and the developing world. And these researchers were looking at trying to diagnose tuberculosis using a chest X-ray. So for the purposes of this talk, let's say that tuberculosis is this blob that I've put onto this X-ray. What the study did was it took a model, or two models actually, and it got them to separate X-rays into either being normal, not worrisome for tuberculosis, or worrisome for tuberculosis. And this model basically went through 3 phases. The first step was training, which is basically taking the model to class, where we showed it which X-rays had tuberculosis and which ones did not. That's called supervised learning. The second phase was what we call validation, where essentially it's like a self-test. Try and see which ones the model was able to get right, which ones it didn't classify correctly. And then there was a final exam, which is about 150 different patients in whom the model had never seen their X-rays before. And then it was tested to see how accurate it was. We use something called an AUC, but essentially that is a metric defining the accuracy of a model. And these 2 models did pretty well. So AlexNet and GoogleNet were their names, and they got between 88 and 90% accuracy. But can we do better? If we take those same models, and before showing them these X-rays, and before taking them to class, on tuberculosis, we get them to sort out those random pictures that we were talking about earlier today, 1.2 million of them in this case. And then subsequent to that, once these models have separated out these pictures and sorted them out and differentiated a plane from a car from a building, we then give them back these x-rays and go through that same 3-step process. Go to class, do your self-assessment, final exam. How do these models do on that final exam? So this is what they did before, but now if we get them to sort random pictures before they do it, all of a sudden the accuracy is 98%. And this is the thing that I think is so fundamentally powerful about AI. These models actually learned something from differentiating a plane from a plant that they were then able to apply to diagnose tuberculosis better on X-ray. And there's no way that I could program or code a model to do that myself. So how are we using this in Calgary, and what kind of research is going on? One of the projects that I'm privileged to work on is involving CT scans with a partner named Altus Labs. And you can think of a CT scan basically as slicing your body like a loaf of bread. And you can look at these slices in different ways. You can look at them end on, or you can kind of stack them together and look at them from the side. And by doing so, you can construct a 3D representation of an organ, for example, the lungs in this case. And so what the model that we're working on does is it takes input data points from a CT scan of the chest. It then does a lot of different complex calculations to try and identify different organs, to separate the lungs from the skin, from the heart, from the bones, and then looks at over 1,000 different variables within that CT scan to then try and come up with a final prediction, which is how long somebody might live with lung cancer. We can then go back to that model and see what was it actually paying attention to. So this is a heat map. And in red is the areas where the model was paying more attention, and in blue is areas it was paying less attention to. Circled are the tumors that we actually knew about, or the primary tumors in those patients. And so you can see that the model was paying attention to those tumors, but also that it was paying a lot of attention to areas that aren't necessarily circled. And this then helps us unpack why the model is making the prediction it does, which is a critical part of this process. This model was able to divide patients into 10 groups. And essentially, the higher the number, the higher the risk of the person passing away from lung cancer. And so I would be much more concerned about somebody in decile 10 than I would be in decile 1. And if we look at 2 specific patients in this study, both of them who are 67 years old, both are males, one was diagnosed with a stage 3 lung cancer, and the other one with a stage 1 lung cancer. And they both got treated with surgery. Normally, for the patient on the right, I would talk about how their cancer was caught early, it was cut out, and that we didn't need to do any subsequent treatment. Whereas for the patient on the left, we would talk about doing more intense treatments after surgery. When we run this model on these 2 patients, what we found is that the person on the left was scored as a risk of 4 out of 10, relatively lower risk. The patient on the right actually got a score of 10 out of 10. And sure enough, when we follow these patients, what happened was the person on the left was alive 71 months later, and the person on the right had actually passed away 9 months after that first CT scan. And so again, we can see that this model was able to see beyond just the stage of cancer to help predict other things that may impact that person's survival. And that would potentially change my approach in the clinic. Because if I saw this, I would talk to that person on the right about trying to be more aggressive with my treatment to prevent this from happening. And that leads to what we're working on now, which is trying to create this concept of a digital twin. Some of you may have seen that Nicolas Cage movie called Next, where he can see a few minutes into the future and work through what happens and then decide which step is the best one to take. And then once he makes a move or has an action, all of the possibilities in front of him change again. And that's essentially this idea of digital twins. You take a patient and create an entire copy of that virtual world. And then as we get more information, new CT scans, new assessments, new blood work, we can then modify the model's predictions over time. This is a complicated process, and so it's a collaboration between multiple institutions, the Tom Baker Cancer Center, the University of Calgary, other universities, Altus Labs, other companies as well, with a lot of support from different government agencies like the Digital Technology Supercluster, as well as support from, essentially, people supporting things like Own Cancer. And this, I think, fundamentally is how we get closer to that crystal ball. So can we predict the future? Not quite yet. A lot of the tools that I've talked about are still years away from being able to be applied into clinical practice. Because again, if we're making predictions like this that have that much weight, we need to make sure that we're getting those predictions right. And so there's a lot of work to be done, but this is what gives me so much optimism about how we can use AI to make better predictions, to try and make some of those difficult decisions a little bit easier for our patients. Thank you.
Thank you, Omar. So our next speakers are going to show us a different way that AI is being used today. And we have, for the first time, I think, in the Cracking the Cancer Code series, a dynamic duo presenting at the same time. Dr. Andrea McNiven is currently the Director of Medical Physics at the Tom Baker Cancer Center and Division Head of Medical Physics. She moved to Calgary in June after almost 16 years in Toronto at the Princess Margaret Cancer Center. And her co-pilot today is Lisa Barbera. She has also been brought here from Toronto, and I think both of them were motivated in no small part by the opening of the new Arthur Child Comprehensive Cancer Center. Lisa is the head of radiation oncology at the Tom Baker Cancer Center and the University of Calgary.
Good evening, everyone. I'm Lisa,
And I'm Andrea.
just so you're clear before we get started. Go to the next slide. So I wanted to start the talk today by starting where I was, or where the field of radiation oncology was when I did my residency training. And so at the risk of giving myself away as the oldest panel member, these are the tools that I had when I got started. I had plain x-rays and I had wax pencils. So what we're showing on the screen here is a plain x-ray of somebody's head and neck area. You can see their skull, you can see their spine, their neck, and then a little bit of shoulder at the bottom, and their jaw and their teeth. And what you may also notice is that there's some drawings on this x-ray. So the radiation oncologist had indicated that she didn't want to be treating through the brain, for example, so she drew a shield with those hash marks across it to say, okay, I want to treat this area in the middle around the throat, but I don't want to treat the brain. People may not be familiar with radiation oncology, but it's actually one of the mainstays of cancer treatment along with surgery and chemotherapy. I know it's a bit of an obscure specialty still, but half of all cancer patients will get radiation treatment after their cancer diagnosis. I think the important thing for everyone here tonight is that it's not like chemotherapy, which is a drug treatment. It goes into the bloodstream and goes all around the body. Radiation is more of a focused, targeted treatment that goes to a specific area, and that's the only place where the radiation has its effect. It does not have its effect on the rest of the body. The radiation beams that we use are the same as what you would have for a chest x-ray. They're just much stronger. And the way the radiation works is that it damages the DNA of the cancer cells, so when those cells try to divide, they're unable to do so properly and they die off. Radiation has evolved a lot since I got started, and you'll get a bit of a glimpse in that tonight. I've distilled the pathway for receiving radiation treatment down into 4 steps. There's probably about 1 million steps, to be honest, but for tonight we have 4. So the first one is patient simulation, which is kind of like a dry run of the treatment. The second step is contouring, where we define the area that we really want to focus our treatments on. The third is planning, where we create a dose map of where the treatment or where the dose is actually going on the body. And then we actually get to the treatment delivery at the end. You'll see as we go through some of these details that there are definitely challenges that we face in planning and delivering radiation treatment. It's a lot of teamwork, which is one of the things I love, but it does require a lot of handoffs between different medical professionals. Every person who's involved usually has a lot of time-consuming tasks that they have to do. All of the work is really technical. We have multiple different software platforms, many different pieces of hardware that are involved. And it's just a fairly complicated process. We have lots of built-in quality checks along the way so that every team member makes sure that we're doing the best to make sure that like every patient goes, as they go through these steps, has a plan that is going to be safe and effective for them. So it's maybe no surprise to hear that radiation oncology or radiotherapy as a field has really been interested in automation of tasks for quite some time. But the advent of AI is really sort of speeding up our ability to develop processes that are more efficient and opening doors to other avenues where we may be able to use this kind of technology. So Andrea and I are going to sort of walk you through these process steps and talk about how AI can be applied to each of them. This is the first step, simulation. We acquire images most commonly with the CT scan, occasionally with MRI, but most typically CT scan. And unlike that X-ray that I showed you at the beginning, the CT gives us three-dimensional information instead of just two-dimensional information. And we have this idea of these bread loaf slices kind of going through so you get a picture of all the anatomy. We won't talk about AI here, but we're going to talk a bit about contouring, which is our next step. So this is a picture of a skull. You can see the eyeballs and the optic nerves are outlined in green. The brain is outlined in orange, and the brainstem is outlined in blue. So after the CT is done at simulation, a radiation oncologist has to go through each and every single one of these bread loaf slices by hand and outline all of the structures that we're interested in. So if we go down a little bit farther, for example, this slice is kind of about here through the floor of the mouth. You can see the tongue, the mandible, your jawbone here on the side is, I think it's outlined pink. The salivary glands, your parotid glands, are outlined in yellow there. And on this slice, we sort of see, so it's looking red, where the cancer is starting to show up, and that green line includes some of the lymph node areas that we're worried about. And then if we keep going further down, now we're sort of at the voice box level, or that bone at the front, the white's the Adam's apple, and you can see we have lymph nodes outlined on either side that are places we want to give dose to. Andrea?
So this is the first time and an example where we are actually using AI in the clinic now for our patients. So since I'm a physicist, I like some numbers. So we've got, for example, over 20 different pieces of anatomy that have to be contoured in the head and neck. And as we talk about those bread loaf slices going down, typically for a patient, we could have 100 to 200 slices that have to be contoured manually, one by one. So you can imagine how time-consuming that is, as Lisa said. So how we're using this in the clinic right now for AI is that as it improves with the algorithms that can look at the patterns in the images and to create information from previous patient treatments, we can implement these AI auto-contouring tools in the clinic. So vendors can now have these automatic tools available to clinics across the country. And in Calgary, we have been validating them to implement them safely and effectively for our patients. So the radiation medicine team tests the contours, as said, looks at the accuracy, verifies that it is saving us time, and can even identify areas that we might expect the algorithms to most struggle with or fail. So in checks and those quality checks we talked about, we can focus on those areas where we think they might fail to make sure that we are still maintaining the accuracy of the treatment. So the team at the Tom Baker Cancer Center has already been able to implement automated contouring tools using AI for patients being treated for brain, head and neck, and lung cancers. And we continue to move forward with validation for more sites as we step through the body and add this for more patients. And so by implementing these AI tools in the clinic, we've been able to decrease the contouring time for normal tissues from 1 to 2 hours per patient down to as low as 15 minutes per patient, even with the detailed review of the contours and any required edits that need to be made. We are drastically improving our efficiency.
So the The next step after the contouring is the planning. We've shifted anatomy now, so we've out of the head and neck and we're into the pelvis. So on this CT slice, we have the hip bones showing on the side. You have the bladder that's outlined in yellow and the rectum that is brown. And then the prostate gland is that organ that's right in between. And so after we create a dose map, it would look something like this. So you can see that the highest amount of radiation, the red, the highest dose is focused primarily on the prostate gland, and it's been shaped best as we can to spare as much bladder as we can at the front and as much rectum as we can at the back. And this plan was created by a person, a manual plan.
So this is another example where we can say we're already using AI tools in the clinic here in Calgary to treat patients. So here we have that manually generated plan that was made by an individual, as Lisa described. And in typical practice, this can take hours or even days to create an acceptable plan for an individual patient. The treatment planning is a very iterative process. So with thousands of parameters that could be changed about how we deliver the radiation, someone creating that plan will change a couple of those parameters at a time, see the result, go back, make some more changes, and keep going through that process until they achieve a good plan for treatment. We have been able to implement automated planning in the clinic, which can now take that down to approximately 10 minutes to generate a plan. So this allows us to achieve that acceptable plan much faster. So as you can see on the right here, we've added this auto plan, and you can see that red high dose area is still centered on the prostate, and we've got some very small differences in kind of the lower doses surrounding it. And this would be similar to if you had two different treatment planners generating a single plan for the patient. So both are acceptable, just slight differences, because there's never necessarily one right answer for a treatment plan. So in Calgary, the radiation medicine team has been able to implement automated solutions for breast and prostate treatment planning at this time, with more development in progress.
So for completeness, I'm showing a picture of radiation treatment. We won't talk about the use of AI in this step today. This particular example shows somebody getting treatment to the head and neck area, and she's wearing a mask to keep her head still during the treatment. So these are just a couple of examples of how AI is already being used in the clinic and helping us with some of the problems that I had mentioned earlier on. I think it is improving our efficiency, our consistency, and our quality. And I think there's countless ways that AI could potentially help us care for patients, but there's a lot of research that's required to figure out how to best do this. So Andrea will tell us a little bit about what's happening in Calgary in that space.
So the medical physics department at the Tom Baker Cancer Center is the home of many graduate students from the University of Calgary. So this collaboration successfully allows us to move forward research projects that will directly benefit our patients in the future. And currently, many of the graduate students are working with different medical physics supervisors on AI projects. So I'm going to go through one of the examples in detail, because one of the projects is looking at head and neck radiotherapy. So the head and neck, as we've talked about already, there's a lot to contour there. And why we contour a lot is because the head and neck is really an area that also gives us a lot of daily functions that we might take for granted. So we use the head and neck to swallow, to taste, to eat, to see, to smell. And since the tumors are often very close in proximity to all of these normal tissues, they do receive some radiation, and that's why some patients have different long-term side effects related to where the cancer is delivered. So if we think about taking information from the simulation images and the contouring that we talked about, so in this example, if we think about contouring muscles that help us swallow, and we look at the plan and what kind of dose might be delivered to that organ or those muscles during it, And then we look at information from treatment outcomes. So what side effects are the patients reporting themselves afterwards? And we can use all of that together to create AI algorithms that will allow us to predict what type of dose might result in what kind of treatment outcomes. And in the future, the hope is that this will allow us to better, even further personalize radiation therapy and have discussion between radiation oncologists, for example, and the patient about what type of side effects might be most important for them to avoid personally for quality of life long term as they survive. So we're getting closer to that with this type of research. A couple of other examples of what our students are working on. One student is looking at AI to look at the simulation part and use different types of imaging, used either in treatment planning or in follow-up, to see if they can use those algorithms to identify patterns early and identify brain metastases earlier so that we can change the potential treatment options for the patient. And two other students are looking at cervix cancer. So specifically, they are looking at different aspects about how we can improve treatment outcomes by improving different steps in the radiation therapy process. So this could include informing decision-making related to how radiotherapy is delivered, which type of delivery is best for which patient, to automate the treatment planning to gain efficiency in that, and also to improve quality, and then combining it all together again to predict that patient's treatment outcome. So essentially using AI to improve every part of the radiotherapy process. So continue to move all of this research forward, we'll need to continue this local collaboration between the university and the Cancer Center, but also collaboration locally, nationally, and internationally to create large, high-quality data sets to create more AI models that can help us improve the treatment of our patients in the future. With the local expertise in AI that we already have, both for research and in clinical implementation, we are excited about our move to the Arthur J. Child Comprehensive Cancer Center later this year, where the radiation medicine team will be able to leverage new imaging and treatment technology to further our research and development in areas including AI. This includes the MR-Linac, as we'll be the first center in Canada to have 2 of these machines. With these, we will be able to move towards the goal of personalized, high-quality, adaptive treatments for each patient.
So what you've seen this evening demonstrates how AI is a tool that we can use to identify individuals who are at risk of developing cancer, to improve our abilities to screen for cancer, to better be able to predict what kind of treatment patients should get to improve their outcomes in the long run, to be applied to radiation therapy techniques to allow us to adapt on a daily basis, for example, as patients come for their treatment. And that in turn creates lots of data that can be used to learn for future patients. And that's important because we want to make sure that our applications of this technology are always at the leading edge. So it may be that some of you are wondering if you're going to have a robot doctor at some point in the future. I'm not too worried about my job personally, to be honest. I can assure you that's not the case. All of these tools require close supervision and oversight from highly trained humans. But I do think that these tools can give us back a little bit of time to spend on things that only people can do, which is actually caring for other people. And that's a big part of cracking the cancer code. Thanks. Sure.
That was so great. Thank you all. There's so many exciting things happening, and I have been talking to a lot of friends and family about this talk this week, and I feel like people have 2 reactions. This is thrilling, or it's really frightening. And I think there's a couple of reasons it's frightening, and people wonder, is it safe? You know, there's a lot of hype, there's a lot of marketing. It seems to be happening from an outsider's perspective, at light speed compared to other advancements in medicine. And so thinking about the history of medicine and how that principle of first do no harm has been there from the time of Hippocrates, how do we sort of make sure that that principle remains paramount now as we bring in this new technology? And that's for all of you. Have at her.
I think from my perspective at least, the project that I talked about, we've actually been working on it for about 4 years to try and make sure that we're addressing exactly what Christina was just talking about. And there's so many different aspects of that question about safety. It actually starts even when we're looking at the data that we're using and how do we protect patients' confidentiality. And so that's been a huge part of the work that we were doing over the last 4 years with Alberta Health Services and the University of Calgary, was trying to figure out how can we get access to the data without compromising patient confidentiality. We don't want a model, for example, to be able to reverse identify someone's identity. That also wouldn't be very useful from at least my perspective, but we don't want that possibility to exist. Then you take kind of that data safety thing and you apply it and say, okay, I have a model that, for example, I showed you 2 cases seem to work. 2 cases isn't enough. And that's why I'm not using that model in the clinic today with my patients. Like I said, we need to test it, we need to validate it. We can say that, yes, this model works on data from patients in Alberta, but the reason that we have a national collaboration is because then we need to prove that it also works for patients in Toronto and Montreal and BC and so on and so forth. And then you gradually build up this whole armamentarium essentially of evidence that, yes, this model is doing what we need it to do, and also that we're addressing sources of bias. And if we're conscious about where we think that bias might be, we can try and address that. The same way that Dr. McNiven was talking about identifying the points of failure in the models that they're using in advance so we can focus more on those. And then the last thing I think that's related to that is when we're combining all this data together and trying to apply it to patients, we need to be able to biologically understand why the model is making the prediction it is. And that's where those heat maps are a really good example of when I can go back and say, well, why is the model, for example, paying so much attention to the muscle mass that a patient has? And then in my head, I can go back and say, well, biologically that makes sense because someone who is malnourished because of their cancer is probably more likely to pass away. And we can see that across medicine where studies, for example, in cardiovascular disease, we've seen that artificial intelligence models will routinely identify things like depression or socioeconomic status that maybe aren't things that we classically thought of as being risk factors for heart disease. We thought of things like smoking or diabetes. But then when you actually go back and realize the model is looking at this factor, we can reverse engineer and say this makes sense. And so I think all of those are key pieces.
And I can add on another topic. So I think from the radiation therapy perspective, highly technical. We already have safety frameworks in place for introduction of any new piece of equipment into the clinic. It goes through this validation and testing procedure, and we can just directly translate that and apply it to the work we do. And I think, too, as we see these new developments, a lot of work is already being done for each of our disciplines to look and see what depth of knowledge about AI do we need to have as different types of medical professionals, and curriculum is being revised already to give future physicians or medical physicists or nurses the tools that they need to do to work with AI in the future, and that's an ongoing process which I think will help us as well.
I mean, I've said well by both of them. I'm not a physician, I'm an epidemiologist, but I think that principle of do no harm also applies broadly to public health, right? And so I think, these models that we want to be able to use, whether it's to identify someone for screening, they need to be accurate, of course, but they need to be safe, they need to be equitable. And I think it might be surprising that the time from the development of these technologies before they're actually in use is a good deal slower than maybe we appreciate. And those breaks maybe seem like a bad thing. Like, we want these tools as quick as possible. But I think those breaks are a good check to make sure that we're doing these things safely. I think we see these tools like ChatGPT or Google calls it Gemini or whatever. They create these tools and then they're just like thrown to the public. And we see all the repercussions and the good and the bad that can come with that. In the healthcare universe, it's really quite a bit different. Testing, validation, testing, validation before this gets into the hands of the people that need to use it. So, I mean, I think that is the way forward to make sure things are safe, is to take our time and to make sure that the tools that we're putting into practice don't, make it good for some people, worse for others, right? This has to be across the board, a comprehensive, equitable improvement to healthcare delivery.
Well, I want to follow on a point that several of you made, and that's talking about bias and risk of bias. And there are concerns that the data that some of these AI systems have been trained on is already biased based on what humans have done and what we have studied. That the algorithms used for melanoma, for example, are done mostly on people with white skin. And I think we're seeing there's similar work being done in kidney cancer that black patients were not as, data from black patients was not as present in the algorithms. And so can you speak to me about how to deal with this risk of bias in AI?
It's a fair question and a totally fair concern, and I think that anyone who works in the field would share that. And I think it comes down to, what patient population or what data set have you used to train your data on, right? And is that going to be representative of the patient population that you want to apply the AI to or the algorithm to? Andrea may be able to speak more to this, but I think that there are, for example, the FDA in the United States is bringing in more regulations when they come through for approval for AI tools, that they want to know how representative is the population that that you've used to create the model or the tool that you're using, to try to break some of that down a little bit. At the moment, I think it's something that we have to have an awareness of and do our best to counter as we move forward. And I think it's also this idea of we can't get stuck. Like, you can't have a bunch of data and create a bunch of algorithms and then use them forever and ever and can assume that they will always be robust. Our technology changes, our understanding changes, the inputs that we might want to have would change. And so I think that there's this kind of evolving, I don't know if a rotating door is the right, but this is evolving process, right? That you have new tests, you have new information about patients, and you have to figure out how to include that information. And I think as we are doing that, we can also make efforts to be more robust about the other variables that we're including. I don't know if you have anything else to add.
No, I think that's it. I think, there's different governance and safety checks that are all getting caught up to the speed that AI is being implemented, that will question kind of commercial solutions and also remind us that we have to keep improving, as Lisa said.
I think just one quick point on that as well. AI and essentially computational processes are evolving just as quickly as medicine is. And so I'm a physician, and keeping up with the changes in oncology is kind of occupying the vast majority of my time already. And that's why we have engineers and people who are experts in this field who are trying to solve those problems. One of the big problems we had before, stuff like bias, was looking at that black box problem of how do we know why a model makes a decision that it does? And now we're seeing more what we call transparent models, where you can actually see through that black box, so to speak, and figure out how they're making their decisions, which then also allows us to say, well, where could those sources of bias be? And how can we actively train a model to avoid that? And so I think the answer to that question, in a way, is actually more data. Because if you can get more data that's more representative, and we're really lucky in Canada because we have public healthcare systems, that we do have a bit wider, more diverse data sets than, for example, a lot of institutions in the United States might have. And so we can use that to our advantage to make sure that we're addressing these sources, but you have to do it from the design of the study onwards. It's not something you can kind of go back and try and retroactively do.
So I've spent a lot of the last year working on electronic health records, and this came up a lot as I was reading up for this talk, that electronic health records can really help us get good data that can help with AI. And so I wondered, looking at the systems we have in Alberta, maybe across Canada, are there things that you would like to see on the electronic health record front that would set us up better for the future when it comes to AI?
Yeah, I mean, I think we're very hopeful that electronic health records can help us push this field forward. I think the challenging part is that the electronic health records are collected for very different reasons. They're to serve patient management and for clinical reasons. Now, we selfishly, in the research world, want to be able to harvest that and use that data in order to improve these technologies. And I think when we see things like ChatGPT, these large language models, I think that gives rise to hope that eventually we might be able to sort of wrangle these health records into meaningful data and that we can support these AI technologies. And again, we're hoping that something like Connect Care, which is rolled out at a province-wide level, can help to support that. I think all of that still remains to be seen, and the future will tell. But I think there's at least optimism there that using electronic health records can be another source of important data to integrate into these pipelines.
And as our health records get better, and Connect Care is a great example of this, there's so much that we can use it for when we design a health record not to just be something that you look back at and read chronologically. And so, now I can actually go and, for a patient of mine, pull up what their blood pressure was 3 years ago in Rocky Mountain House, which is actually really, really cool. And so that gives us a lot of data, but it also brings up a lot of those other concerns that we talked about. How do we protect patient confidentiality? How do we do these things safely? And I'll give Alberta Health Services a lot of credit in that they've been spending a lot of time and energy and resources in trying to make sure that our health records are now designed in a way that they hopefully can be used for research and that they can make patients more a participant in their own research as well, in terms of being able to opt in or opt out of things in the future. But then also making sure that all the research is being done safely.
One thing came up, Matt, that during your presentation. Do you see other kinds of cancers being screening for other kinds of cancers because of AI in the next couple of years? Will we see screening for pancreatic or kidney cancer?
I mean, one of the things that, when you were asking that question, what it made me think of is medical imaging is a standard part of healthcare, not just in cancer or in cancer screening, but we do medical images all the time. And often you're seeing things in those images incidentally that are unrelated to the reason you're getting that image in the first place. Lung cancer is a space that we see that all the time. People maybe come in and get an X-ray or CT for a different reason, and maybe you identify a heart abnormality on a lung screening CT or vice versa. So I think these more comprehensive approaches of, can we use these images maybe beyond just their original, the original reason they were ordered. And I think there's optimism there that some of these cancers that, pancreatic, very lethal cancer, can we do better? Can we use images? Can we use AI? Maybe. I think a lot still needs to be fleshed out there, but I think there's optimism there.
And with that, we need to make sure we're also not doing harm. And so I often tell the story. I was going to a conference in Chicago, and I got into a taxi, and they knew that it was a cancer conference. And so the cab driver was excitedly telling me about how he got a CT scan just because. And they found 3 or 4 things. So he went and had 3 different procedures. And each one of those things that was removed was benign. And so in his mind, he's like, it's great. We found these 3 things. I had these 3 procedures. And in my mind, I was like, you went through 3 unnecessary surgeries, each of which could have had a complication. And so we need to find that balance where we're finding things that we need to find, but we're also not causing problems by chasing after things that we don't need to find.
So I'm going to ask one more question, and then we'll open it up to you for your questions. So you start thinking about what you want to ask. But I want to ask each of you, 5 years from now, maybe 10 if you need the extra runway, what breakthroughs do you expect in cancer care because of AI?
From a radiotherapy perspective, I would hope to see a lot more robust implementation in our clinic. So we're just sort of starting with this contouring, just starting with the plan. I think there is such a huge opportunity for us to not just have this for certain parts of the work that we do, but have it for all of the parts of the work that we do. And, I would love to see that we have a built-in system that would just perpetually be able to use the data that we're generating from our clinical work to help us, predict how to do the care better, or tell us how to do that care better for the next patient that walks in the door. And having an infrastructure like that, that would be my hope. Maybe not quite a direct answer to your question, but I think it's possible. Yeah.
And I guess to add the technical side of radiotherapy, I think right now we take, one CT sim, traditionally a CT scan prior to treatment, and patients will come daily for treatment, for a week or even up to 7 weeks of treatment. And you can go through a lot of changes anatomically in that time. You can lose weight. The tumor can shrink, it can grow. By having these kind of daily images and more AI tools and faster processes, we'll be able to implement, hopefully, routine adaptive treatments that allow us to better target the tumor only and adapt for those changes on kind of a resource manageable way that is not achievable for us right now without AI.
I think my dream would be to be able to sit down with a patient and say, knowing everything that we know about your tumor and combining so many different things like your CT scan images, your pathology slides, your blood work, your height, your weight, maybe even more details about the genes that are driving a cancer to grow, or the proteins, or the metabolic environment, or the immune environment, combining all of these things to say, we've run essentially a bunch of simulations, and we know that with this % certainty, this is the best treatment to give you right now. And then after we give that treatment for a few weeks or a few months, we can then say, okay, now we've revised the model, and this is the best next step. And especially to be able to, in my mind, be able to do that for rarer tumors. Like I treat breast cancer, which is very common, and we can get these big data sets, but I also treat sarcoma, which is incredibly rare. And we can get a depth of data. We can learn a lot about those tumors over time, but we're never going to be able to get thousands of patients onto a study for those tumors. And I think that's where I would really hope that we can apply these tools using the depth of knowledge to try and come up with answers, again, to questions that are really, really hard to answer, which is, which of these two treatment options that theoretically have the same success rate should I be doing?
For me, I mentioned in my talk that lung cancer screening was different than these other screening programs. And one of the ways it's different that I didn't talk about is how young it is as a program. When we think of like cervical cancer screening, the Pap test was invented in 1928. The first provincial screening program in BC was in 1960. Breast cancer screening started in the late 80s, colorectal cancer screening in like the early to mid 2000s. The first piece of evidence that showed us that we can screen for lung cancers was in 2011, and the second corroborating clinical trial came out in 2020. So really the clock has started since 2020 that we have evidence that we can do this. And so by comparison, lung cancer screening is a very young program, but I think we're excited that it's coming up at the same time that AI is coming up. And so maybe the growing pains of getting provincial screening programs up and running, maybe AI can help in the implementation and optimization, and so we can get lung cancer screening to the status of these other excellent provincial screening programs.
Thank you. All right. I think we probably have house lights. And I think we also, I can't see, but I think we have 2 people with microphones. I see some movement at the top. So if you have a question, just raise your hand. Oh, there we go. Raise your hand, be really exuberant about it, and one of our people with microphones will come find you. I do see one here.
Thank you all for your talk tonight. It was so exciting where we are right now. It kind of seems a little bit Wild West on new tools that are coming out. I just, for all of you, want to know kind of what is the balance of new tool development versus commercial tools available for what the research programs that you're working on right now? And if you are developing new tools, who owns the intellectual property? How do we ensure that the tools being developed are going to be available in a public space?
I can kind of start with that. So the tool that we're developing right now, again, a big part of that 4-year process that we've been going through involved Alberta Health Services and the University of Calgary. And one of the big pieces of that was exactly that question that you're asking, because if we're using the data from Albertans to train these models, we need to make sure that the results of these models are actually accessible to Albertans. And so there's stuff I can't say about it for legal reasons, but essentially there are these agreements in place, and that was one of the huge things in there, was how do we make sure that if a tool that is useful is developed out of this, that even if it does become commercialized, we can actually essentially pay it back to Albertans whose data we used. And I think that's true across the board. That's also part of why it's so important for us to be participating in the development of these types of models. Because if you let it happen to you, I gave the example of that Oncotype test. We pay this company out of California every single time we do one of these tests, right? And it's not cheap, shockingly. And so it is really important that I think as much as we can, we try and democratize this type of information so that we can get these resources in a more financially sustainable manner. And if we're not at the ground level, so to speak, in there developing these tools, participating in these things, and actually leveraging the advantage that we have with a huge data set, with a large population, with good longitudinal follow-up. If we don't leverage that, then we're definitely going to run into those issues. But I feel like we're actually making strides in the right direction.
I guess I can add on to that just from the tools we are using in the clinic since we showed examples. Those are vendor tools right now that we are using. I think for radiation therapy, since we use a lot of different computer systems or software, we have requirements where really those need to be Health Canada approved and validated for use in the clinic. So for us, those tools are available now. Originally, some of those tools, you would assess them and they probably weren't at a quality that was good enough to actually help you routinely in the clinic. But now, as models have improved, there are Health Canada approved ones that we can test and implement in the clinic. So I think, it's great if you have generating your own models, but sometimes it's also using the tools that are out there because that might allow you to implement them faster as well to change workflows.
I would just add one little thing there. Like, you used the term Wild West, which was funny because I was thinking that too. When like AI burst onto the scene, it really was like the Wild West. Tools were being developed faster than we could even use them, and people, were saying, "Oh, we need to throw these into the clinic." And it's now being more recognized that these statistical models are like medical devices, and they're being regulated as such, as was just mentioned, with like FDA approval and things like that. So sometimes there is a benefit to not reinventing the wheel, to using commercial or existing services, because a model that you develop today, maybe you could get it in the clinic, 5 years. I don't know how long it would take. But sometimes there is a benefit to embracing existing technologies versus wanting to develop, sort of homegrown solutions. It's sort of a fine line there.
I have a question about prevention, but also spinning off your idea. I had a ultrasound of my prostate, which was fairly routine, which revealed a stage 2 kidney tumor. That was I couldn't believe how detailed they could get down to finding the type. I think they can even DNA test the tumor or exactly find the tumor. So my question is about prevention. I was shocked that there was no bubble sheet to fill in, no data collection. At a younger age, I was exposed to significant occupational hazards with toluene, benzene, things like that. And I wondered sometimes if maybe some of these very specific types of cancer, mine was like chroma, I can't remember the exact name, a chroma type cancer of the kidney, couldn't be also through big data tied in with specific risk factors that the patient might experience through their lifetime. But like I said, I was surprised there was no bubble thing to fill out. There was no survey of who, my background or what I've experienced. And so prevention might be, my question is why there isn't more done to collect data. And again, Alberta's great at digital information, but I think we might be missing something for understanding where these unique and very specific cancers might come from epidemiologically. Thank you.
I would just say a little bit, like I mentioned in my talk, that screening is one of the best ways we can reduce the impact of cancer. Prevention is the best way, right? The best way to not have any problems with cancer is to never get it. So I think to your sentiment of like, should we be doing more data collection? Should we be looking more into prevention and risk reduction to avoid cancers? I would just say, like, wholeheartedly, I agree.
I think a couple of pieces of that. One is, I don't know if you've heard of something called the Tomorrow Project. So it's a massive project in Alberta, another really awesome project where I can't remember the exact number of people, but it's a substantial number of Albertans where essentially they volunteered and they're being followed longitudinally. to see what happens, not just from cancer, but like heart disease and other diseases. And they've been answering those bubble sheets that you were talking about throughout this. And I think a big part of that is the quality of any model that we make is dependent on the quality of data that goes into it. And so we need to make sure the data is accurate. Like a good example is diet studies. Like most people don't remember what they ate yesterday, right? Let alone what they've been eating over the last 10 or 15 years. And that's a problem, right? Because then you can fill out the bubble sheets, but it doesn't necessarily give us that information. I think as technology gets better and it becomes more mainstream and our phones are collecting information and our watches are collecting information, maybe we can start to merge that data with some of our health outcomes data. But again, we have to do it in a way that's safe, and I keep coming back to that, and that's where the challenge is. Like Facebook knows a lot of health data, like a lot of health data. Right? Because people are posting about what conditions they have. People are like looking things up, and then the devices are providing information, right? But taking that and actually applying it then to patient care is an entirely different challenge, because we have to get it right when we do it. And so that's one of the challenges there, but it's certainly something that we're working on. And like I said, projects like the Tomorrow Project are worth looking into because they're really trying to do that.
Is this working? Good. Okay. Thank you very much. I have a question on sort of a different area with your work as a physician, and that's dealing with the explosion of information that's coming along. And I know it increases every single day. You talked at the beginning about ChatGPT. Do you see potentially in a few years something like that, a tool that might be able to help you if you have specific questions to have synthesized the research data that's in existence to provide you with a better beginning to your looking at a specific question, or maybe because of the power, as you were talking with the diagnostic images, finding something different than what you expect, if it can help you in some areas like that.
I was just going to say one thing. I was actually joking with Dr. Brenner about, does everyone remember those pictures, you know, what the future looked like in 1950? And there's like flying cars and like robot butlers and stuff like that. I always try to keep in mind that we're good at building technologies. We maybe aren't so good at like projecting about how things are going to look in the future. I mean, I think absolutely those like those large language models, things like ChatGPT, they're going to have a role to play in some way. I don't know if I have a vision for the future. Yeah, I would leave it at that.
Yeah, my only comment was that one of the limitations of AI, I think, is this idea of context. There's still a layer of interpretation, like for something like I have this kind of cancer and I don't know what kind of treatment, like, and putting that into ChatGPT or a similar kind of tool. There have been quite a few studies that have been done. I think ChatGPT managed to pass some kind of medical licensing exam. I don't remember the details. We did a study where we, gave ChatGPT some challenging clinical cases, like how would you treat this kind of cancer, and to see what, and we all looked at the answers to sort of say, well, yeah, actually that looks kind of reasonable. But in reading them, there were always these like kind of slightly odd things that would come out that, you'd sort of wig you to the fact that maybe this wasn't the human that gave the answer, this was a computer that gave you the answer. So I think, probably for some basic elements, at least the way the technology is right now, there's some elements, maybe it's like reasonable enough, but I think that there's a lot of context for interpreting what you get back that's always like sort of specific for the patient that's would make me loath to rely on that as like the sole source, right? Yeah.
And I totally agree with that as well. I think you really need to know what the model you're using is actually designed to do. So one of my fellows, we were looking again at a sarcoma, which is an extremely rare cancer, and we were trying to figure out what treatment to do. And he texted me at like 9 p.m. to be like, I cannot find this paper, which seems to like perfectly answer the question. And I was like, well, where did you hear about this paper? And he'd asked ChatGPT just out of curiosity, and it had come up with this perfect citation for a paper that doesn't exist. And the reason is because ChatGPT is a language model, and its job was to essentially come up with what would the answer look like if it existed. It wasn't to check whether or not that answer existed or not. And so, I don't use things like ChatGPT, but can we use something like that if it was purpose-built for that? Yes, I think we could. Right now, we're not there.
I think we might have time for one question, maybe two if it's a fast question.
Thank you. Oops. Okay, I think we're good. Are we good? Yeah. Thank you. This was fascinating. And thank you, Dr. Omar. I was one of your patients in 2019. The question that I have, is it possible, dreaming, if AI could be developed in such a way that if you go to the doctor for a general, if you can use AI to test for everything, and you go through one of those screens that you would go through a metal detector at the airport, and it would flag everything that you have, and that would address a bunch of stuff, immediate, short term, or even in my case, I'm 4 years now, and would my cancer ever come back? So that would be wishful thinking, but
I think it's called
if
the
you can think
tricorder.
it, hopefully it can happen. Thank you.
If it does, I'd probably have to open up a food truck or something. But honestly, I do think that working towards that goal is something we should be trying to do. Because again, like we talked about with prevention, the earlier we can find conditions, the more we can do to modify things. I think it's definitely a stretch goal or a moonshot, if I'm being honest. But that's not to say that we can't try to go for that.
Did we have one more question up at the back?
Hi, I just have a quick question about, you talked a lot about validation and testing. So who actually is responsible for the validation and testing? And in terms of radiation oncology, would that increase the work for radiation oncologists that are currently in practice? I'll start that and then you can tie in. So I think it's really a team. So I think in radiation therapy, it's a big team. So radiation oncologists, radiation therapists, medical physicists, and it really probably depends a bit on what the implementation is about who is all involved in the testing. So often medical physics takes one role in kind of running through multiple patients, using different metrics to assess, but there's also a role for radiation oncologists to do that double check and also verify, like, would I accept this? Is clinically this okay? So it might look slightly different for different technology. Your second part, I think, was, does that take more time away from other work? I think we've got to be conscious of balancing that the time, but I think right now, the once it's implemented, it is saving us time. So that's part of the reason we're doing this, site by site, because it does take time to validate it. So by stepping through the body, for example, we have time to do that. The time savings potentially from the one site that's already implemented could then be used to work through the next site. So I think it's a balance that we're still learning.
Yeah, it's like there's an initial investment of time up front to get that development work done and do the validations. As a radiation oncologist, maybe there is a bit more time up front to do these comparisons side by side. Yep, those look like contours I would draw, and yep, that looks like a plan I'd be happy with. But once that's completed, then you're kind of, you're getting all that time back down the road, sort of going forward.
So I think we're actually a little bit over, and I'm sorry, I know there were a few other questions here. But I want to start by thanking the four of you. Thank you so much. I think these have been really excellent talks. We all learned a ton, so thank you. And I want to thank all of you for coming out and always being so engaged. It's just such a treat to see so many people who want to come out to learn about AI in cancer care. A few more thank yous. Thank you to the Charbonneau trainees who always show up with all your enthusiasm back there, and to the Calgary Public Library for allowing us to host our 7th event. to the Charbonneau Leadership and Community Engagement Team for championing this series. And the last notes here are, I think the next event for the Cracking the Cancer Code series will be in the fall. So if you watch the Arnie Charbonneau Cancer Institute, their social media, they will be posting the details on the next event. So once again, thank you all, and please come again. Get home safely.